which one? Start recording. Okay, yeah, started. Okay, so G1 is pi sigma square A by E. So this I told you, displacement components and polar coordinates, all these things. This I will tell you later. Okay, this I will tell you later, because this has to be covered only after the stress intensity method has to be explained. Then only these things will be appropriate to understand. Otherwise, it's very difficult. Only thing you should know, this is the crack, no? So in the crack vicinity, suppose this is the crack. Okay, so any point we can find the displacements, that is a ux, uy, and uz. Okay, ux, uy, uz. This uz will come only certain cases, not both the cases, because you may wonder, no, it's a two-dimensional. It is basically two-dimensional because it's thin structures. So plane stress, plane strain. Only the uz will come because of plane stress condition. So it is nothing but the displacement. It is nothing but the displacements at this particular location. Okay, suppose this is u. This one means this is x direction displacement, y direction displacement. How much because of the okay, that we will, once we come the stress intensity approach, then you will understand better. So in terms of the location can be identified in terms of r and theta. This is okay, polar coordinate system, r and theta. So I can locate at any point with respect to its r and theta. Suppose this is r and this is theta. Suppose I have a point here to know about displacement. If this is the point, it will have r and theta. This is theta. Okay, so r is the distance. So likewise, you can see plane strain, you don't get this one, u z. Plane strain you don't get. Okay, these are all the fundamental mechanics part. Okay, why I'm getting in plane stress uz quantity, whereas in plane strain I'm not getting and all. It is already explained to you when you in the mechanics part. Now there is a relation between K1 and G1. Okay, so here also I will touch upon something like very briefly. I will go through that, not deeply. I will not go. But there is a relation existing between energy release rate and shear intensity factor, SIF, energy release rate. So there is a relation available. You can relate. Okay, either you can go from here to here, or you can go from here to here. How to get that particular relation? Let us see right now. So here is the okay specimen, or this is the crack. The crack is subjected with the load sigma. Okay, this is something like it's a quite big, but for the display purpose, we made it very close to that. Otherwise, it's something like a very big plate. So this condition is plane strain condition. I hope you know very well what is plane strain and plane stress. Okay, suppose what you call that? Something like I have a thin strip. Okay, something like a thin strip subjected with the internal pressure. Then this is plane stress. Plane stress. Okay, a thin strip subjected with the internal pressure, it's a comes under plane stress. What is plane strain? Then plane strain means, suppose I have a tube, thin tube, but it's a quite length. Okay, thin tube. I'm taking a piece of that, again subjected with the internal pressure. Then it is a plane strain. Similarly, suppose I have a dam, reservoir. It goes kilometers. Here the water. Okay, this is the ground. This is what? Water. This is the structure to stop the water. So it goes kilometer. So if I take one strip, this is I'll cut one strip from this. That is one strip with a very thin structure. Okay. This is very small strip I took. Very small strip, unit strip. If I analyze, because this analysis is holds good for the entire length of the cross section. That one strip I can do, I can apply the load. Okay, whatever load I have. Then this is plane strain. Plane strain. Okay, I hope you distinguish the. It's a something like 2D, but as a dam reservoir, as a whole, it is, say, this is X. Let us say, suppose this is Y, this is a Z. It's a three-dimensional analysis supposed to be. In reality, your complete structure is a 3D analysis subjected with the internal the pressure, water pressure one side, something like that. But the structure is something like uniform, maybe a kilometer. The water also standing, it exerts the same pressure. Then you need not take the entire 1 kilometer structure as a 3D and to analyze it and find the solution. Not necessary. That is where actually we are simplifying from 3D solutions to 2D solutions with the appropriate boundary condition and so. But that conversion comes under plane strain approach. Plane strain approach. What is plane stress? A thin structure subjected with, suppose a very thin structure. I have a very thin structure, very thin. It is subjected with the forces. This is 2D, basically 3D, but it is a small dimension in this particular direction, comparatively X and Y. Z direction is very small. Okay, that change I need not take it into consideration. Then it will become 2D. But what is the nature is plane stress. This is plane stress nature. So plane stress nature, there will be chance of third direction displacement. That is what you will get UZ. But the UZ, though we have considered the Z direction responses are all 0, but still you will get the UZ means it is the resultant of X and Y's component. That only makes the UZ. Otherwise, you have idealized no response in UZ or no strain in UZ, no stress in UZ. That is a direction, Z direction. But still you are getting displacement means what? It is the resultant of X and Y's effect. See, these are all the intricacies in the two-dimensional approach, the conversion from 3D to 2D. So these things are all what I would say. Basically, you supposed to learn these things in your previous analysis or previous structures, your previous subjects. Here in fracture mechanics, we are using those concepts. That is what, okay, because the entire process of fracture mechanics comes under plane, that is a two-dimensional thin structures only. Why? Because 3D, we are not giving much importance on the fracture. Because it's a structure itself 3D, it will have so many resistance for the development of the cracks and so on. But still, we have the systems to be analyzed in 3D structures, but we are giving more importance on thin structures having the flaw, thin structures having the crack, thin structure is having the fracture, thin structure is having the discontinuity. I hope you understood. If you take the composites for a typical aircraft wing, it's about 3 mm. Skin, I'm talking. The wing, skin, 3 mm composite. But if you see the structure in that 3 mm, there'll be something about 20-30 layers of the composites film will be there. Each 0.15 mm, something like that. This 23 mm divided by 0.15 mm, 20 layers you will get it. When within that particular 3 mm, 20 layers of composites. So any one layer having discontinuity, then it is sufficient for the crack to expand. So again, that comes under 2D analysis. I hope it is clear that, okay, what is plane stress, what is plane strain analysis, both are comes under two-dimensional analysis procedure. I hope you know 1D, 2D, 3D. Basically, every structure in reality is three-dimensional structures only. Based on the convenience or based on the available in conditions, available boundary conditions, we can convert from 3D to 2D or 1D. Why we are doing this kind of conversion? Easiness. Okay, solution is very easy. Okay, solution is easy because in 3D structures you supposed to find 6 unknowns: sigma x, sigma y, sigma z, tau xy, tau yz, tau zx. Whereas in 2D you are sufficient with 3D, three dimension, three responses sufficient with respect to stress. Sigma x is sigma y, tau xy. Even in fact in 1D, still you are bothering about only sigma x. So your you are actually what you call that complexity in structure or resolution finding things will be easy when you convert from 3D to 2D or 1D. But you cannot convert everything into a structure is given. Simply you cannot analyze with 1D because of my solution easiness. Not possible because you supposed to have the appropriate boundary condition existing in the structure. Then only you can convert it into 2D or a 1D. Okay, otherwise it's a 3D only. But when you go for 3D, you have to solve complex mathematics with the six equations, 6 unknowns. But whereas in 2D, 3 equations, 3 unknowns. So your solution will be quicker, easier. These are all the basic stuffs you're supposed to know in the mechanics field. Okay, mechanics field. Now coming to this problem, because you should not confuse that the what you call that plane stress, what is that plane strain. Hereafter you should not confuse because the entire fracture mechanics sitting on these things only. Okay, two-dimensional systems only. We will see 3D also, but only very minimum theory we will study. How a crack propagates in 3D system and all, we will see that. But it is very much useful in 2D, very much useful in 2D structures. I hope I have, okay, I made you to understand that the importance of 2D structure, plane stress and plane strain. Another method of simplification of 2D is the what you call that axis symmetric structures. Okay, there are 3 ways you can convert it into 3D to 2D: plane stress, plane strain, axis symmetric. That we are not dealing now. Axis symmetric. Axis symmetric also similar to this only. மேம் நான் இன்னொரு 10 minute half an hourல கூப்பிட்றேன் மேம், மீட்டிங்ல இருக்கேன். ஓகே, ஹலோ, நான் ஒரு half an hourல கூப்பிட்றேன்ப்பா, ஒரு மீட்டிங்ல இருக்கேன். So now let us see the relation between K1 and G1. This is stress intensity factor. This we will in a detailed way we will see soon. But here, since you have the um, energy release rate stuff with you right now, we can easily discuss this relation. Then we can see in detail the K1. This is energy release rate. This is stress intensity factor. So how to get this particular relation? That is what we are going to see. So now I told let us take a plane stress structure, 2D structure, wherein you have your crack is there. The subject, the component is subjected with load sigma, and let us you can assume that the crack, what you call that crack growth mechanism, because of the fatigue. Now let us assume, okay, this crack from here it is actually moved from the first delta t from here to here. I'm sorry, I'm very bad at it. Okay, the crack got moved. I told the crack growth mechanism. Crack came here, and so this supposed to come here. This supposed to come here. I'm sorry. Like this. So what happening now? Okay, what I'm doing is this is one delta t. Okay, or delta, not delta t. It's a delta a. Okay, this is one delta a because okay, crack means one delta a. Then your crack will blunt and it will become sharp. So this is your new crack, something like that. So this is one delta a we are going to discuss here. Okay. Now take a crack of length a plus delta a. That's what a plus delta a. Use Q as the reference point for finding displacement. When you finding displacement, you can use this edge as the reference. Now, what I'm saying is, you have to imagine, okay, this is my crack. In this crack has actually moved to the extent of delta A, so that this will come here. Now, what I'm saying is, I'm going to give an force, additional force, extra force by sigma y, okay, a compression. I'm trying to close this particular crack. It is an imagination. Okay, you have to imagine a crack has developed and it will become big. So I'm giving an additional force sigma y in this fashion. Why? Because I need more force on this side and less force on there. That is what this is reducing nature, this sigma y. Okay, I'm giving, this is the imaginary force I'm giving to close the expanding crack. This is the your imagination. Del t equal to 0 time frame, you are imagining. I'm considering a crack a plus delta a. So the delta a will bulge. So I'm giving a force, pseudo force or imaginary force, a delta y in this fashion. So that time it's a compressive force because it's expanding. So if I give compression, this crack will close. So you have a tendency, okay, healing in brittle materials. Okay, when you in the brittle material, what will happen once you give additional compression, the created crack will heal. That is the beauty of brittle nature of material. Okay, so here you have to use Q as reference point for the displacement monitoring, and the P is the the location, that is inner end of the crack is the finding stress. Let us see. Okay, now K1 is the, I told you, stress intensity factor for crack length A. K1 plus delta K1 is the stress intensity factor for A plus delta A, because there are two cracks. Okay, this is A plus delta A crack. This is A crack. So A crack would like to, I can find K1 for here, I can find K1 for here. So this is what the K1 is for this particular thing, K1 plus delta K1 for this case. Okay, so now, okay, this is your crack length A, and this is your complete crack length delta A, additional growth. Here I am just looking a small crack length called DS consideration. Okay, suppose I have a this one is there, this is line, this is the X means I can take some dx no in the solution process. Similarly, we have taken ds. Where is the ds is taken? From S distance it has taken. S distance it has taken. Now, okay, along this particular delta A, okay, at a distance S, okay, at a point S, the displacement, okay, I just want to get the displacement. So, okay, what is my theta? I told you, no, I can locate any point with respect to its r and theta in the stress intensity factor. Okay, the theta is what? It is a pi. Theta is pi because for displacement, Q is the reference point. So I have to take this as the theta. Theta can be here means it's a theta. If theta is here means this is the theta means phi is the theta. Theta can vary from 0 to pi. Then what is my r? R means the distance, no? Delta A minus S. Delta A minus S. So this is my R. And the pi is my theta. This is Westergaard. Already I have introduced this man, Westergaard. Okay, you will see in detail later, but you should know like Irwin or Griffith or English. Westergaard also one important scientist who has invented a lot of things in the fracture mechanics. Now, okay, so you can take a plane stress structure. There you have a crack. You are applying the fatigue load. Because of the fatigue load, the delta A has become. So in that situation, I am closing the crack by applying a stress sigma y. In this particular fashion, why that particular fashion means I need more stress at this particular point, less stress at this point to close the crack. So here the locations are all identified, P and Q. And in that particular location, I am finding my displacement Uy. Okay, for that I need R and theta. So R is this quantity is delta A minus S. Pi in the theta is the pi. I hope you're all clear. If you have any doubt, you can stop me and ask me. So simply substituting this R and theta value in my original equation, in this equation. Okay, plane stress equation. Okay, K1 by G or something. In this equation, I'm substituting these values. I'm getting this value. Because that equation in terms of theta and R, once I substitute those values, that equation will become like this. Okay, this is the displacement at that particular point. Now I want to find the stress. What is the formula to find stress? What is the formula to find the stress? Okay, the stress formula, it is not given so far, but you can find the stresses because here given only the displacement, not stresses. So the sigma y already, okay, you can find. I will tell you when you put here in the similar solution you will get, okay, but I could not locate right now. You will similar solutions also there to find the sigma x, sigma y, tau xy. So in that particular equation, same, it looks similar equation only that I will show you later. You put the values of r and theta, but here you can see r equal to theta. Because why? The theta is 0. Why? Because uh, for stress, P is the reference point. For displacement, Q is the reference. So P is the reference point means your theta is 0. But in this point, Q is reference point means theta is pi. Okay, I hope you got it. Similarly, here R is S. Earlier it was R is sigma ms because here this is the reference point in stress. You put those values in that equation, you will get sigma y as K1 by root of 2 pi s. What is K1? Stress intensity factor. What is S? Distance. What is pi? All you know very well. Okay. Now, the total elastic work required by sigma y. Okay, total elastic work required by sigma y in closing the crack is equal to the energy release rate, balancing energy. Because how much I supposed to apply the stress or energy because of the stress means how much the resisting force, isn't it? No, that much only I supposed to put. So what is the resistance force? G1 into B into delta A. G1 into B into delta A. Okay, so now I'm balancing these two things. Okay, balancing these two things. G1B delta A is the resistance. Okay, this is the energy. Sigma y into Uy is the energy. You hope you know, I hope you know that, no? Strain energy is what? Half into sigma y into Uy. This is the energy, but I'm getting total energy. I need to integrate from 0 to delta A. Okay, because I have two surfaces, something like that. So this is the energy base. This is the resistance energy. This is the strain energy creating because of this particular system. So B is the thickness of the plate. So in this equation, I have sigma y equation. I have Uy equation. I have Uy and I have sigma y. Once you substitute, okay, in that equation, your G1 will become, okay, delta A tends to 0. That means you have to work for very, very smallest increment of crack. Okay, you will get this particular equation. Okay, in this particular equation. So in this particular equation, you can neglect delta K because it's since you have considered delta A is small, you can easily knock out this particular fellow. So this will become, you will get G1 is, that is energy release rate is K1 square by 1 plus mu into pi into G into delta A into integral log quantity of this. Okay, mathematically, I can put S is equal to delta A into sine square alpha. This leads to my G1 equal to K square by 1 plus Poisson's ratio into pi into G plus 0 to pi 2 cos square alpha by D alpha. Okay, cos square alpha by D alpha. So by solving the integral and substituting E is equal to this elastic relation, you know very well, E equal to 2G. This equation will become G is equal to K square by E. E is, okay, the G1. So this is the relation. Energy release rate, stress intensity factor. Okay, suppose I have this. This is material parameter. I can get this. Suppose I have this, I can get this. This is for the mode 1. But you have to be very careful. This relation is valid only for brittle materials. This relation is valid for only brittle materials. Suppose I want my model is plane strain approach means then my relation between G1 and K1 is I need to add 1 minus mu square. Suppose if it is Mode 2 and mode 3. For mode 2 relation, G2 is equal to K2 square by E for plane strain, and 1 minus mu square this one plane strain. Similarly for G3 and the K3 relation is okay for this. Okay, K3 square by 2G. Because here you can see G will come. Why G is coming? It's a shear modulus. Because the tearing stress. It is the tearing stress. It is dominated by the G. The 1 and 2 is dominated by Young's modulus because it's a slip and mouth opening. So E is sufficient to model. Whereas in G, why G normally they use relate with thing means it's a tearing stress. That is a shear modulus. Sometimes it is important when you define the G. So this is the relation existing between the shear energy release rate and the stress intensity factor. Here how we are doing that? Okay, we have a structure. A structure is having crack expansion. So we are applying a force, an equivalent force to close the crack. So we are using that particular relation through which we are extracting the relation between G and K. G is the energy release rate, K is the stress intensity factor. And we have extended that mode 1 relation to mode 2, mode 3 by similar theory. Suppose in any crack propagation, I have 3 modes are existing means, okay, then I have to add all the 3 modes, G1, G2, G3. It's not necessarily in every crack will have only one component. I told you some time back. It can be any 3 cracks combination, crack modes combination. Okay, the response can be all the 3 modes. Sometimes it may take place. Okay. So these things I will take up later. Now I can stop it right now. If you have any doubt, you can ask me.
Sir,
Mm.
so this method is used only for brittle because when we are applying force, the crack closes.
That healing.
So what will happen if the same is performed in ductile materials, sir?
Ductile material basically this relation basically works for brittle material. So where really these kind of relations are all useful means in general, okay, practical point of view, why I need this particular relation. Normally, that is very important. Practically, why I need this. In reality, I want to analyze a structure. Then I should get whether I'm going for energy release rate approach or I'm going for stress intensity approach. There one thing. When you talk about, because there are different models you can take up. One is, I told you, energy release rate, stress intensity factor, COD method, or J integral. Okay. Now, our discussion so far only energy release rate only. So, in the energy release rate, when you deal for energy, it's very difficult to suppose something like what is the the design process. It is a very simple mechanism that my G1 should be less than G1C.
Yes, sir.
Okay, this is the simple, ultimate simple logic to be checked. But getting this one is a big process. Okay, getting G1 is process. So this is material parameter. How can I get this particular parameter? So when you getting these from stress easy.
Yes, sir.
Getting energy, critical energy from the SIF, this is easy process to get this one. In this process, you will get KIC. From KIC, I can get GIC through this relation. You got my point?
Yes, sir.
That extent only this relation is useful. Okay.
Yes, sir.
In that aspect only, these are all useful. Because when you search for a material, for your material you want to analyze, I want my G1C means, but internationally, people might have done K1C, K1C for the same material. Okay. In
Okay,
your
sir.
hand, you will have only K1C. Why? Because it's easy. Always stress approach, easy to deal, rather the energy approach. So through stress approach, people will find you for the same material K1C. So I want to perform in energy, but I'm having a stress value. How I can compare? So you can use this relation to get this one. You got it? What I'm saying?
Yes, sir. Got this one,
That's it.
sir.
That's it.
So then the ductile materials, then it will act differently, sir. Then.
Ductile material, I don't come for G. Ductile material, I will straight away use with K. K1 compared with
Okay, sir.
K1C.
Yes, sir.
K1 compared with K1C.
K1C.
I told you, K1C is abundantly available for a material.
Yes, sir.
Abundant data.
Mm.
Whereas in energy dealing only sometimes we will problem.
Okay, sir.
Finding the material value, stress-based approach always easy than the energy-based approach. Whereas basically one point in time, you will simply ignore the energy release rate. You
Yes,
will
sir.
be more attracted in stress intensity approach. Okay.
Yes, sir.
Then what happened later? This was the story 1940, 50s. People were fond of energy release rate. Then Irwin came and he found 60 to 80 stress intensity approach. Then later on, J. Rice came. He found the J integral. It is energy based approach. That is the top of these two things.
Okay, sir. So
J
then
integral is
maximum we will take J integrals, the integrals are short.
yeah. Finally, we will reach there. But without knowing this, you can't do anything there.
Yes, sir. Yes, sir.
Okay.
Got
These
it,
are
sir.
all the fundamentals. How J, okay, Rice found J integral means through this only. Once you know this only, you can deal there.
Yes, sir.
You supposed to know this and that because sometimes J integral also you once you find once you know come across J integral, it's energy release rate. But how that energy release rate to be found? It is through stress. Okay, it is through
Stress.
stress. Those things, these fundamentals are very much useful to them.
Okay. So then from this J integral will come.
Yeah, G integral is when you struggle like this much, when you come there, you will feel only this much. Why I struggle this much? That in that sense, the J integral looks like very nice and versatile approach.
Okay, sir.
But practical point of view, stress intensity approach is very important.
Yes.
Practical, experimental point of view. Experimental point of view, fracture mechanics, K is good.
Yes, sir.
Using the same K methodology, you can use in J also. Same procedure you can use in J also. But J is an energy-based approach. Okay. I hope
Okay,
I
sir.
am not confusing you.
No, sir, sir.
Okay.
Got it, sir.
Okay.
Yes.
Okay, ma. Any more doubts?
No, sir.
Okay. So anything you can ask me. Okay. It's a forum or it's a things you can clarify, because now you're all highly senior now. Your next level is you are entering to market or entering to real-time domains. So you have to clarify so many practical aspects. Then it will be easy for you to get into the stream. Okay, you can use this platform for those purpose. Okay.
Okay, sir.
Fine. Have a good day.
Sir, portion
Sir,
for midterm.
thanks.
Pardon, ma?
Midterm portions.
Yeah, till the last day of that particular thing.
Okay.
Tell this one, sir. This energy.
Yeah, when is your midterm, ma?
Starting from 7th, sir.
You are 7th. Okay. But your midterm is when, ma? Your exam?
But this
You
will
was
be
on? Anyway, we will check it. Okay.
okay, sir.
So
Okay.
it is on 13th, sir.
Monday, next Monday, isn't it, ma?
Yes, sir.
What is the mode, ma? It is again 50 marks, no?
I think so, sir. I'm not sure about the mood.
Okay, ma. Okay, ma. We will clarify it, all those things. Okay.
Okay, sir. Okay,
Right.
sir.
Right.
Thank you.
Thank you, sir.
Okay.
Thank you, sir.